Let us move on to the two other measures of variation for a given distribution. The second and third variation measures are the variance and the standard deviation. Very grossly stated, these are the mean gap between each value and the mean of your distribution. We'll come back and precise that after we've been through all the steps to calculate it. Here's how you would calculate the variance of the painkiller A dataset. We will assume here that we are dealing with a population. Step 1 is simply to calculate the mean of your data. As we've seen before, to calculate the mean, we add all of the values in our dataset and then divide the result by capital N, the number of values in our population dataset. Step 2 is to subtract the mean from each value in your dataset. So we start with the first value, 9, to which we subtract 10, gives us -1. Second value is 9.5, to which we subtract 10, gives us -0.5. And we continue for all of the values. Step 3 is to square each result you got in step 2. So -1 squared is 1 hour squared, -0.5 squared is 0.25, 0 squared is 0, and again, 0.5 squared is 0.25, and 1 squared is 1. You might be wondering why you are squaring these results. We'll see in the next step. Step 4 is to find the sum of the squares you just did in step number 3. So if we add all of the squares we had in step number 3, we come up with a total of 2.5 hours squared. If you had not squared in step number 3, this sum would have been equal to 0. You can try it here if you don't believe me, but you can also try for any other distribution. Now, because we have negative numbers, the sum of our differences, difference being the result of a subtraction, comes up to 0. But we're not looking for the mean difference. We're looking for the mean distance, so the mean gap between each value and the mean, which is why we cannot have negative values into our sum here. This is why we are squaring every result to make sure we do not have any negative distances. Step 5 is to divide the sum of the squares you got in step 4 by n, which will actually give us the variance. So we divide 2.5 square hours by 6, which will give us a variance of 0.42 square hours. Step 6 is to find the standard deviation. To do so, you must simply square root your variance. So in this case, square rooting 0.42 hours squared gives us 0.65 hours for our standard deviation. Why do we use the square root and not the variance? Well, remember that we squared the distances in step 3. By doing so, we have squared our units as well. So we went from hours to hours squared. By square rooting the variance, we return to our original units, which was the hour. So what is the true definition of the variance and of the square root? The variance is the average, or actually the mean, of the squares of the distances each value is from the mean. Notice how in the equation there is a sum on the top and the number of values on the bottom portion. This looks remarkably like the equation for the mean, doesn't it? Well, then let's break this down further. First, when we have a population, variance is symbolized by sigma squared. Then, step 2 is where we actually take the difference between each value and the mean of the population. And then we square each one of these differences, which is step 3. We then add the sum of the squares together, which gives us step 4. And we divide our total sum of the squares by the total number of values in your population. That's step 5. As we know already, the standard deviation is simply the square root of the variance, which leads to the main distance between each value and the mean of the distribution. As such, the only differences in the equation is the symbol for standard deviation, which is now sigma and not sigma squared as it was for the variance, and the square root, which, in the way it is noted, square roots the whole equation. When we are talking of variances and standard deviation for samples, there are a few variations in notation. Notice how the variance symbol is not a Greek letter anymore, but instead is a Roman S, which is squared. The symbol of the mean returns to the symbol for the mean of a sample, and instead of dividing by capital N, we are dividing by lowercase n, to which we subtract 1. We subtract 1 because samples, mainly smaller ones, have a tendency to underestimate the population's variance. So by dividing by a slightly lower number, we greatly reduce this bias. As for the standard deviation, we notice the same differences. So we go from sigma to S for the symbol of standard deviation, and instead of using Greek letters or capital N's, we go back to symbols for samples. So changing from Greek letters to Latin letters indicates that we are dealing with samples and not populations. How are variance and standard deviation reflected in our distributions? Remember that these are measures of distance between each value and the mean of the distribution. So the larger the standard deviation or variance, the more spread out our distributions are. Let's take a look at these two bell-shaped histograms. Notice how these graphs are both centered on 200, so it's safe to say that they have the same mean. Which one would have the greatest standard deviation? That would be the one on the right. Notice how this graph is much more spread out than the one on the left. See how the values go from lower than 50 to higher than 350, whereas on the left graph, the values are much more concentrated around the mean. When your distribution is bell-shaped, you can apply the empirical rule, also known as the normal rule. This rule tells us that there is a certain amount of our values that are found within standard deviations from the mean. This rule says that there is 68% of all of the distribution values within one standard deviation of the mean. It also states that there is 95% of all of the distribution values that are within 2 standard deviations of the mean. Finally, it says that there is a whopping 99.7% of all the distribution values within 3 standard deviations of the mean. Let's translate this in something a bit more tangible. Imagine that you are planning a road trip with one of your friends throughout Quebec. You know that gas prices will be an important part of your budget, so you want to check the variations in gas prices. So after checking out some of the prices, you calculate that the average gas price in Quebec is $1.25 per litre, and that the standard deviation is of 7 cents per litre. The empirical rule states that 68% of the gas prices you'll encounter will be within 1 standard deviation of the mean. In other words, you can add 1 standard deviation to the mean, so $1.25 plus 7 cents gives us $1.32, and subtract 1 standard deviation to the mean, which gives us $1.18 per litre. So 68% of the gas prices you'll encounter will be between $1.18 and $1.32 per litre. You'll find 95% of the gas prices between 2 standard deviations, so multiply the standard deviation for 14 cents, and then add and subtract 14 cents to the mean, giving you the limits where you'll find 95% of gas prices. Multiply the standard deviation by 3, add and subtract that result to the mean, and you'll find the range of values where you'll find 99.7% of the gas prices you'll encounter during your road trip.